A magnetic field large enough to swallow our galaxy exists. We have found one even larger. This is the story of the largest magnetic field ever discovered, a cosmic force of unimaginable scale. By the end, you will understand how this invisible giant reshapes our entire picture of the universe. What forged a magnet spanning millions of light years? And what does its silent power control in the dark reaches of space? How does it feel to know the cosmos is threaded with forces we are only beginning to see? That invisible giant begins with a simple, everyday force. A magnetic field is a region of space where a magnetic force can be felt. It is an invisible influence, a kind of cosmic architecture built by motion. At its heart, every magnetic field is created by moving electric charges. Think of the electric current flowing through a wire or the churning of molten metal deep inside our planet. That motion generates the field. You can see its effects by sprinkling iron filings around a simple bar magnet. The filings will not scatter randomly. They will align themselves into beautiful, curving arcs, tracing out the lines of the invisible force. These lines show the direction a tiny compass needle would point, flowing from the magnet's north pole to its south pole. The density of these lines represents the field's strength, which scientists measure in units called Gauss or Tesla. Earth's own magnetic field, our magnetosphere, is a perfect example of this power on a planetary scale. It is a vast, teardrop-shaped bubble generated by the dynamo of Earth's molten core, and it serves as a vital shield. It deflects the constant stream of charged particles from the sun, the solar wind, protecting our atmosphere and making life possible. This is why magnetic fields are not just scientific curiosities. They are fundamental architects of the cosmos. In astronomy, they shape entire nebulae, sculpting clouds of gas and dust into fantastic pillars. They control the jets of matter screaming from black holes. They are the powerhouse behind pulsars, the lighthouses of the galaxy, whose intense beams are powered by unimaginably strong magnetic fields. To understand the largest one ever found, we first had to understand this basic, universal language of force. Our planet's magnetic field is a gentle embrace compared to the monsters that lurk deeper in space. The first true cosmic powerhouses are magnetars. These are the collapsed cores of massive stars, neutron stars, but born under such extreme conditions that their magnetic fields are almost beyond comprehension. A magnetar's field is not merely strong, it is a quadrillion times stronger than Earth's. To put that number into perspective, if a magnetar were as close to us as the moon is, its magnetic force would be strong enough to strip the information from every credit card on the planet. These fields are so intense they can literally twist the star's solid iron crust, causing starquakes that release bursts of gamma rays visible across the galaxy. They are the ultimate cosmic magnets, but they are also remarkably small, only about the size of a city. Their power is concentrated into a terrifying, dense point. Then we scale up. At the heart of most galaxies, including our own Milky Way, sits a supermassive black hole. While the black hole itself may not have a magnetic field in the traditional sense, the maelstrom of matter swirling around it certainly does. This orbiting disk of superheated gas, the accretion disk, is a dynamo of unimaginable violence. Charged particles whipped to near light speed within it generate magnetic fields that are not just strong, but also incredibly organized. These fields can funnel material into powerful jets that shoot out from the poles of the black hole, extending for thousands of light years into intergalactic space. These jets are visible across the universe, beacons of magnetic power on a galactic scale, but the canvas grows even larger. We find that space between galaxies in a cluster is not empty. It is filled with a thin, super-hot gas, and threaded through this entire vast structure are magnetic fields. These are the largest coherent magnetic structures we knew of for decades. They are incredibly faint, millions of times weaker than Earth's field, but they are spread across millions of light-years, connecting hundreds of galaxies in a single, invisible web. They are the quiet background hum of the cosmos, shaping how gas flows and how cosmic rays travel. So we had our hierarchy, the intensely powerful but tiny magnetar, the organized jet-driving fields of black holes, and the immense diffuse fields of galaxy clusters. Each one seemed to represent a natural limit, a ceiling for magnetic influence at its particular scale. The stage was set and the record book seemed complete. Then we pointed our telescopes at the true void, the space between the clusters themselves, and found something that rewrote every assumption. The space between galaxy clusters was supposed to be a quiet frontier. It was in this profound emptiness, in the data from a collection of galaxies known as the Abell 3391 and Abell 3395 clusters, that the record shattered. The discovery was not made by a single person in a eureka, a moment, but through the meticulous collective work of an international team. Scientists from institutions across the globe were using a revolutionary tool, the low-frequency array, or lofAR. This is not a single-dish telescope, but a vast network of thousands of small antennae spread across Europe, all working in concert to act as one gigantic, ultra-sensitive radio eye on the sky. Their target was the faint, ancient glow of radio waves emanating from these distant clusters. What they were looking for was a specific fingerprint within that radio light called polarization. Think of light as a wave vibrating in all directions. Polarization is when those vibrations are forced to align in a single plane, like sunlight glinting off the surface of a lake. In space, magnetic fields can cause this alignment. The team, led by researchers from the University of Hamburg and other institutes, began to map this polarization across an immense swath of sky. The initial data was puzzling, then astonishing. They expected to see the polarization signatures confined to the clusters themselves, tracing the known, faint magnetic webs within them. But the signal did not stop at the cluster edges. It kept going. Delicate threads of polarized radio emission stretched far out into the supposed void, connecting the two clusters across a staggering distance of 10 million light-years. This was the clue, the visible tracer of something invisible. The polarization pattern was a direct map of a magnetic field structure. The only explanation for such a vast, coherent signal was a magnetic field of unprecedented scale, one that enveloped not just the clusters, but all the seemingly empty space between them. The realization was gradual, built on cross-checking data, ruling out other sources, and running complex simulations. When the evidence became undeniable, the team published their groundbreaking paper. The announcement sent ripples through the astrophysics community. They had found a magnetic field so large it made previous record holders look provincial. This was no longer a feature of a galaxy or even a cluster. It was a feature of the cosmic web itself, a fundamental thread in the fabric of the universe. The quiet frontier was not quiet at all. It was humming with a force we had just learned to see. The Colossus has a name, and it is not a single object in the traditional sense. The record-breaking magnetic field was discovered within a vast cosmic structure known as a filament. This specific filament is the bridge of gas and dark matter connecting two galaxy clusters, Abell 3391 and Abell 3395. Located in the southern constellation of Norma, this filament is part of the Great Cosmic Web, the large-scale structure of the universe where galaxies are strung along invisible threads like pearls on a necklace. But this particular thread is threaded with something extraordinary. The magnetic field detected by the lofAR team is woven throughout this entire filamentary bridge. Its scale is almost impossible to grasp. The filament itself stretches for an astonishing 10 million light-years from end to end. To understand that distance, consider that our entire Milky Way galaxy is only about 100,000 light-years across. This single magnetic structure is 100 Milky Ways laid end to end. It does not just surround galaxies, it dwarfs them, enveloping the entire superhighway of matter that links two of the universe's largest metropolitan areas. The first visual evidence came not in visible light, but in the subtle language of radio waves. The initial maps from the low-frequency array revealed something breathtaking. Instead of showing isolated blobs of radio emission from the clusters, the data painted long, delicate tendrils of polarized light. These tendrils were the magnetic field's signature, tracing its lines of force across the void. The visualization looked like a cosmic fingerprint, or perhaps the delicate strands of a spider's web illuminated by a distant sunrise. It was a map of the invisible, revealing a force of nature operating on a canvas larger than anything we had ever measured. This was not a magnetar's intense scream, nor a black hole's focused jet. This was a deep, resonant hum echoing through the bones of the universe itself. But how do you measure a force field spanning millions of light years? The answer lies in a ghostly light we cannot see with our eyes, a signal born from particles trapped in the magnetic web itself. This light is called synchrotron radiation. To understand it, picture an electron, a tiny charged particle caught in the grip of a magnetic field. The field does not pull the electron in a straight line. Instead, it forces the electron to spiral, to corkscrew along the magnetic field lines. And just as a skidding tire emits sound or a spark crackles with energy, that spiraling electron must shed energy. It does so by emitting radiation, a specific type of radio wave. This is synchrotron radiation, the faint but unmistakable cry of a particle whirling through a magnetic maze. Across the vast filament between the galaxy clusters, countless electrons are doing exactly this, each one a microscopic lighthouse broadcasting the field's existence. Our telescopes do not see the magnetic lines directly. They collect this chorus of radio whispers, but the mere presence of this radiation only tells us a field is there. To map its shape and gauge its power, scientists must listen to two specific qualities of the signal, its polarization and its intensity. Polarization is the key to direction. The radio waves emitted by these spiraling electrons are not random. Their vibrations are aligned by the very magnetic field that guides them. By measuring the precise orientation of this polarization across the sky, astronomers can trace the invisible architecture of the field, line by line, revealing whether it is tangled, ordered, or stretched into vast sheets. It is like seeing the wind made visible by the aligned ripples it creates on a pond. The intensity of the radiation, its sheer brightness in radio frequencies, then reveals the field's strength. More intense synchrotron radiation generally means more electrons spiraling more violently, which points to a stronger underlying magnetic force. By combining these two pieces of evidence, the oriented whisper and its volume, and by knowing the distance to the filament, researchers can perform a cosmic calculation. They can estimate the field's strength even across that mind-numbing gulf of 10 million light-years. The number they found is almost absurd in its contrast. While the field is unimaginably large, its strength is remarkably faint, 1,000,000 times weaker than Earth's protective magnetosphere. This is the heart of the achievement, a testament to incredible precision. Detecting such a whisper-thin signal from across the universe is like trying to hear a single snowflake land from a mile away, while filtering out the roar of a nearby city. It requires not just powerful telescopes, but exquisitely sensitive instruments and algorithms capable of separating this cosmic fingerprint from a fog of background noise. Every data point in that beautiful map of filaments is a triumph of patience and technology, a measurement of the seemingly immeasurable. This magnetic whisper is measured in units called microgauss. 1 microgauss is 1/1,000,000th of the strength of Earth's magnetic field at its surface. The field threading the cosmic filament is estimated to be just a few microgauss in strength. On its own, that number seems insignificant, almost laughably weak. But the true power of this structure lies not in its intensity, but in its staggering volume. Think of it like this: a single candle flame is intense and bright in a dark room, but it cannot light up an entire city. Now imagine billions upon billions of candles, each one just a faint ember, but spread uniformly across that entire city. Their combined glow would outshine the sun. This cosmic magnetic field operates on that same principle of unimaginable scale. While each point within it is a faint whisper, the total amount of space it fills is so colossal that the energy stored within it becomes almost incomprehensible. To put a number on that cosmic energy, scientists have made calculations that defy easy belief. The total magnetic energy contained within this single filament, this one thread of the cosmic web, is estimated to be equivalent to the combined explosive energy of billions of supernovae. Let that settle for a moment. A single supernova, the death of a massive star, can outshine its entire galaxy. Now multiply that cataclysmic force by billions, and you have the quiet, humming energy reservoir locked in this invisible structure. Its physical scale is just as mind-bending. We said the filament is 10 million light-years long. To visualize that, picture our Milky Way, a majestic spiral of 100,000 light-years across. Now line up 100 of our galaxies, one after another. That chain would only get you 1 million light-years. You would need to repeat that process 10 times over to span the length of this magnetic bridge. It is not a feature within the universe, it is a fundamental feature of the universe's architecture. When you compare it to every other magnetic field we know, the contrast is profound. The Sun's magnetic field, which drives solar flares and the beautiful aurorae on Earth, is powerful but confined to the solar system. Earth's field is our protective blanket. A magnetar's field is a concentrated point of apocalyptic power. But this filament's field is something else entirely, a vast, diffuse ocean of force whose total content dwarfs them all through sheer immensity. It redefines what we consider a powerful magnetic object, proving that in the cosmos, patience and scale can be a greater source of power than ferocious intensity. This immense structure is not an isolated phenomenon. The leading theory suggests we are looking at a fundamental feature of the universe's very architecture, a magnetic field painted directly onto the skeleton of the cosmos. That skeleton is the cosmic web, a vast network of dark matter and hot gas that forms the largest structure we know. Think of the universe not as a random scattering of galaxies, but as a colossal three-dimensional spiderweb. At the intersections of the web's threads, where the gravitational pull is strongest, we find the dense knots of galaxy clusters. But the true majesty lies in the filaments themselves, the long, delicate strands that connect those knots across billions of light-years. These filaments are not empty. They are highways of extremely thin, superheated gas, threaded with the invisible mass of dark matter that provides the gravitational scaffolding. For decades, we saw this web through the galaxies that lit up its nodes and strands. Now we are beginning to see its magnetic signature. The theory proposes that these filaments are not just passive structures but active cosmic engines. As matter flows along these vast gravitational rivers, it does not move smoothly. It creates turbulence, colossal shocks, and shearing motions as different streams of gas collide and merge. Just as motion in Earth's core generates our planet's magnetic field, these turbulent motions in the filament's hot, ionized gas can generate and amplify magnetic fields on a truly cosmic scale. It is a process of weaving force into the fabric of space itself. The weak seed fields, perhaps left over from the universe's earliest moments, get stretched, twisted, and supercharged by this endless flow. The magnetic field we detected is likely not a singular object, but a standard feature of these intercluster bridges. If this theory holds, then the entire cosmic web, every filament connecting every cluster in the universe, could be humming with its own faint magnetic whisper. We have simply found one of the clearest, most detectable examples. This transforms our understanding of the cosmos from a collection of luminous islands in a dark sea to a unified dynamic structure invisibly threaded with force. The darkness between the galaxies is not a void, it is a canvas, and magnetism is one of the fundamental brushes that has painted the universe we see today. The discovery of this colossal filament raises a fundamental question about its very nature. Is this magnetic field a primordial fossil or a cosmic engine? The answer rewrites the history of the universe itself. One compelling idea is the primordial hypothesis. This suggests the field is not a recent creation, but a relic, a whisper from the universe's fiery birth. In the first fractions of a second after the Big Bang, during a period of hyper-expansion called inflation, quantum fluctuations could have imprinted weak magnetic seeds across the entire infant cosmos. As the universe expanded over billions of years, these seed fields would have been stretched and thinned, but not erased. They would be woven into the fabric of space-time itself, a background hum present everywhere. The filament's field, under this view, is simply one of these ancient fossils, magnified and made visible by the vast structure it inhabits. The evidence for this is its incredible coherence and scale, aligning perfectly with the filament's shape as if it were painted on at the beginning. If true, it means we are not just looking at a magnetic field, but at a direct imprint of creation, a snapshot of the universe's first moments frozen in lines of force. The implications are staggering, offering a new tool to probe the physics of the Big Bang itself. Yet there is a powerful rival theory, the dynamo hypothesis. This argues the field is not ancient but self-made. Within the filament, the hot, ionized gas is not still. It flows, it collides, it creates turbulence. This motion, much like the churning of Earth's molten core, can act as a natural dynamo. It could take any tiny, pre-existing magnetic seed, perhaps even a primordial one, and amplify it exponentially through its chaotic motion over billions of years. The field would be a product of the structure's own life and evolution, generated and sustained by its internal activity. The evidence here is the field's clear alignment with the filament, suggesting it was shaped by the same flows that built the cosmic bridge. The challenge for the primordial idea is explaining how such an ancient, all-pervasive field could remain so coherent without being tangled into oblivion by the universe's violent history. The challenge for the dynamo is providing enough energy in that thin, diffuse gas to power an amplification of this magnitude. This is not merely an academic debate. It is a choice between two radically different histories. Is the magnetic web a ghost from the dawn of time, or the breath of the evolving cosmos? The answer determines whether magnetism is a foundational layer of reality, or a beautiful, emergent consequence of its structure. Our detection of this single, titanic filament may have just given us the first clue to decide. To answer that profound question, we turn to the universe's most powerful laboratories, which exist not in space but inside silicon and code. Supercomputers around the world are now running the most ambitious simulations ever attempted, trying to rewind time and build a cosmic filament from scratch. These are not simple animations, they are full-scale universes in a box, governed by the unbreakable laws of physics. The process begins with a digital seed, a representation of the universe a mere instant after the Big Bang, filled with the faint ripples of dark matter and the primordial soup of particles. Then, with a press of a key, time begins to flow forward, but at a breathtaking, accelerated pace. Over months of real-world computation, these simulations enact 13.8 billion years of cosmic evolution. Gravity pulls dark matter into a vast cosmic web, gas flows into the filaments, and galaxies spark to life at the intersections. But the true magic happens when scientists add the final, crucial ingredient, magnetohydrodynamics, often shortened to MHD. This complex term simply describes the physics of how magnetic fields and moving fluids, like the superheated gas in a filament, interact and influence each other. Including MHD in a simulation is like turning on a new force of nature within the digital cosmos. The visualizations that emerge are breathtaking. You can watch as faint, wispy magnetic seed fields, represented by delicate blue and red lines, are caught in the gravitational currents of the forming web. As vast rivers of gas begin to flow along the filaments, these magnetic lines are not erased. Instead, they are stretched like cosmic taffy. They are twisted into braids by turbulent eddies. They are amplified by the sheer kinetic energy of the universe's largest structures taking shape. In some simulations designed to test the primordial theory, the seed fields are present everywhere from the very first moment. You can watch them get pulled and focused into the filaments, becoming coherent threads woven into the fabric of the web itself, a fossil finding its home. In other simulations testing the dynamo theory, the seed is almost negligible. Yet, as the gas churns and shocks ripple through the filaments, you witness the birth of magnetism from motion. The simulations show magnetic fields growing from nothing into the faint microgauss structures we observe, generated entirely by the cosmic engine of the flowing web. These digital universes are our testing grounds. By comparing their final magnetic maps against the real one observed by lofAR, scientists can ask which simulated history looks more like our own. Does the data match a universe painted with magnetic fields at its birth, or one that spun them from chaos over eons? Each run of the simulation is a possible past, a clue to whether we are seeing a ghost or a living breath. The filament's magnetic field is more than a cosmic curiosity. It is a hidden architect. Its gentle but pervasive influence may have shaped the very galaxies we see in the night sky. To understand how, we must go back to the beginning of a galaxy's life. Galaxies are born from the cold collapse of vast clouds of hydrogen gas within the cosmic web. This gas must flow along the filaments, funneling into the gravitational wells where galaxies form. But this flow is not smooth, it is chaotic and turbulent. A magnetic field woven through the filament, even a weak one, can impose a subtle order on this chaos. Think of it like a hidden rail system. The magnetic field lines act as gentle guides, channeling the streaming gas, preventing it from scattering wildly. This could make the delivery of raw material to a growing galaxy more efficient, potentially accelerating its growth and leading to the formation of more stars earlier in cosmic history. The field may also suppress the most violent turbulence within the gas clouds themselves. Just as a magnetic field can contain the superheated plasma in a fusion reactor, the cosmic field could dampen chaotic motions, allowing denser, colder clumps of gas to form more easily. These clumps are the nurseries for stars. By quieting the storm, the magnetic filament could be a silent midwife to stellar birth on a colossal scale. Its influence does not stop at galaxy formation. It extends into the bustling metropolises of galaxy clusters. Within a cluster, galaxies are not stationary. They zip through a sea of superhot gas at thousands of kilometers per second. This motion should create immense wakes of turbulence, like a speedboat churning water. Yet, observations show the gas in clusters is often smoother than expected. The pervasive magnetic field threading the entire structure from the cluster core out along its connecting filaments could be the reason. It may act as a cosmic dampener, a web of invisible springs that absorbs and redistributes this turbulent energy, preventing it from tearing the gas apart. This would regulate the temperature and density of the cluster's atmosphere, which in turn controls whether gas can cool and fall into galaxies to form new stars. In this way, the largest magnetic field ever discovered is not a passive backdrop. It is an active participant in the cosmic drama, a fundamental force that may have guided the assembly of galaxies, moderated the climates of clusters, and left its fingerprint on the brightness, the shape, and the very population of stars in the universe. We are only beginning to read that fingerprint, to see how the invisible hand of magnetism helped sculpt the visible cosmos. Perhaps its most dramatic role is as a cosmic superhighway for the most energetic particles in existence. This vast magnetic filament might be the universe's ultimate particle accelerator, solving a mystery that has puzzled scientists for over a century. The mystery involves cosmic rays, which are not rays of light at all, but atomic nuclei, protons, and heavier elements hurtling through space at nearly the speed of light. The most common ones come from our Sun or from supernova explosions within our galaxy, but a tiny fraction of these particles possess energies so absurdly high they defy explanation. A single one of these ultra-high-energy cosmic rays carries the kinetic energy of a professionally thrown baseball, all packed into a subatomic particle smaller than an atom. For decades, their origin was a profound enigma. Nothing in our galaxy seemed powerful enough to launch them. They had to come from beyond the Milky Way, but what cosmic engine could possibly be that strong? The colossal magnetic fields threading intergalactic filaments are a prime suspect. Picture a charged particle, a proton, entering one end of this 10 million light-year magnetic corridor. The field does not capture it like a cage. Instead, it acts as a guiding tube. The particle spirals along the magnetic field lines trapped within the vast structure. As it travels, it does not lose energy easily in the near-perfect vacuum of intergalactic space. More importantly, the filament is not a smooth, static tunnel. It is filled with shock waves and turbulence from the colossal flows of gas that built it. Each time the particle crosses one of these shock fronts, it gets a kick, a burst of energy like a surfer catching a perfect wave. Over millions of years and across millions of light years, the particle can be shuttled back and forth, gaining a tiny bit of speed with each crossing. The sheer scale of the accelerator is its power source. While a human-made collider like the Large Hadron Collider accelerates particles over a distance of 27 kilometers, this natural one operates over distances 100 trillion times longer. That immense travel time allows for countless tiny kicks to add up, eventually propelling a handful of particles to those impossible ultra-high energies. When they finally escape the magnetic highway, they streak across the universe as the mysterious messengers we detect. If this theory is correct, then these faint magnetic whispers are not just shaping galaxies. They are the unseen cannons firing the most powerful bullets in the cosmos, and we have just begun to map their barrels. Detecting a whisper across 10 million light-years is an exercise in cosmic patience. The magnetic field signal is not just faint, it is drowned out by a cacophony of other radio noise. The primary challenge is the sheer weakness of the synchrotron radiation it emits. Remember, this field is 1,000,000 times weaker than Earth's. The radio waves it produces are like a single, quiet note played in a stadium during a rock concert. To hear it, you need an instrument of extraordinary sensitivity tuned to the right frequency. That instrument is the low-frequency array, a telescope unlike any other. Traditional radio dishes struggle with these ultra-low frequencies, below 200 megahertz, where Earth's own ionosphere acts like a blurry lens, distorting the signals from deep space. LOFAR bypasses this by using thousands of simple, fixed antennae spread across Europe. By combining their signals with supercomputers, it creates a virtual radio dish hundreds of kilometers wide, with the sensitivity to pick up the universe's quietest hums. But even with this power, the data is a mess. The biggest contaminant is our own Milky Way. The space between the stars in our galaxy is filled with charged particles and magnetic fields, which also emit synchrotron radiation. This foreground glow is billions of times brighter than the signal from the distant filament. Separating the two is like trying to spot the faint, consistent glow of a single firefly hovering in front of a massive, flickering neon sign. The breakthrough came not just from better hardware, but from revolutionary software. Scientists developed advanced algorithms that could meticulously model and subtract the complex, patchy emission of our galaxy from the raw data. It is a process of digital archaeology, carefully brushing away the bright foreground layers to reveal the ancient, faint structures beneath. This required mapping the Milky Way's emission in unprecedented detail. understanding its polarization at these low frequencies and having the computing power to process petabytes of observational data. The final image of the magnetic filament was not a single photograph. It was a statistical masterpiece, a pattern of confidence emerging from years of noise removal and signal integration. We did not find this giant because we built a bigger telescope, but because we learned to listen more intelligently, to filter the universe's roar and finally hear its deepest, quietest breath. The discovery of this magnetic whisper was only possible because we learned to see the universe in a new color, a color invisible to our eyes. This is the domain of low-frequency radio astronomy, a realm where telescopes like the low-frequency array listen to the deepest hums of the cosmos. lofAR's design is a radical departure from the classic image of a giant dish pointed at the sky. Instead, it is a vast network of over 20,000 simple antennae spread across stations from Ireland to Poland. These stations are connected by high-speed fiber optic cables, allowing a supercomputer to combine their signals and create a single, virtual telescope with a collecting area equivalent to a dish 300 kilometers wide. This immense size grants it incredible sensitivity to the faintest signals, but its true genius lies in its vision. lofAR operates at frequencies below 200 MHz, capturing radio waves with wavelengths from 1 to 10 meters. At these frequencies, we are not seeing hot stars or dusty nebulae. We are seeing the cold, magnetic skeleton of the universe. It is uniquely tuned to detect the synchrotron radiation from electrons spiraling in weak magnetic fields, the very process that painted the filament's map. Furthermore, its wide field of view allows it to take in enormous swaths of sky at once, essential for mapping structures that span far larger than the Moon. And crucially, every antenna is built to measure polarization with exquisite precision, reading the alignment of those radio whispers to trace the invisible lines of force. lofAR is not alone in this new endeavor. In the remote outback of Western Australia, the Murchison Widefield Array, or MWA, performs a similar symphony. Built on a radio-quiet reserve, it listens to the same low-frequency sky, its data providing independent confirmation and adding depth to our magnetic maps. These telescopes are not just instruments, they are portals. They have opened a window on what astronomers now call the magnetic universe, revealing that magnetism is not a side effect of cosmic structures, but a fundamental ingredient woven into their very fabric. And this is merely the beginning. On the horizon is a project that will redefine our perception entirely, the Square Kilometre Array. The SKA, currently under construction in South Africa and Australia, will be the largest radio observatory ever built. Its name comes from its total collecting area, which will eventually exceed 1 square kilometer. Its sensitivity will be such that it could detect an airport radar on a planet orbiting a star tens of light years away. For the study of cosmic magnetism, the SKA will be a revolution. It will map the magnetic fields of the entire cosmic web with a clarity we can barely imagine, tracing their evolution from the early universe to the present day. It will see the magnetic seeds from which galaxies grew and watch how black holes and supernova inject magnetic energy into intergalactic space. With the SKA, the faint hum will become a detailed chorus, and the magnetic universe will step out of the shadows, revealing itself as a dominant character in the story of everything. Is this colossal filament a cosmic oddity or the first of many giants? The answer is not yet written in the stars, but astronomers are now conducting a grand census, scanning the skies for similar signatures. The discovery in the Abell clusters was a landmark, but a single data point does not define a rule. It could have been a rare, perfect alignment of conditions, a magnetic storm in an otherwise quiet sea. To know for sure, we must look elsewhere. Teams around the world are now pointing instruments like the Low-Frequency Array and the Murchison Widefield Array at other known galaxy clusters and the faint bridges that connect them. They are searching for that same telltale whisper of polarized radio light stretching into the void. Each new observation is a test. If they find nothing, the record-holding filament might remain a magnificent anomaly for decades. But if they begin to find more, if other threads of the cosmic web also glow with this faint magnetic signature, then everything changes. A second detection would be a revelation. A third would confirm a pattern. A handful would rewrite the textbooks. Finding these giants to be common would mean that the vast, empty-looking spaces between galaxies are universally threaded with this invisible force. It would suggest that magnetism is as fundamental to the structure of the cosmic web as gravity itself. The universe would not merely contain magnetic fields, it would be magnetized from its largest scales down. This would settle the great debate about origins, strongly favoring the idea that these fields are primordial, woven into the fabric of space-time from the very beginning, or amplified so efficiently by cosmic dynamics that they become a standard feature of all large-scale structure. Every new filament mapped would add another chapter to the story, revealing how this hidden architecture guided the birth of galaxies and steered the most energetic particles across the cosmos. We are on the cusp of knowing whether we found a cosmic unicorn, or simply the first clear glimpse of a herd that has been there all along. The invisible web of magnetism may be intertwined with the universe's greatest mystery. We have traced its lines through the hot gas of cosmic filaments, but what about the dark matter that forms the very skeleton of those structures? Could these colossal magnetic fields interact with the substance that makes up 85% of the universe's matter? This is the frontier of theoretical physics, a place of fascinating, unproven possibilities. Dark matter, by its very definition, does not interact with light or the electromagnetic force in any way we have yet detected. It does not emit, absorb, or reflect radiation. It reveals itself only through its immense gravitational pull, bending light and holding galaxies together. For it to feel a magnetic field, it would need some form of electric charge, however tiny. Most standard models of dark matter assume it is completely neutral, like a cosmic ghost passing through walls and magnetic fields without a trace. Yet, the sheer scale and coherence of the magnetic structures we are finding invite a daring question. What if some component of dark matter is not entirely dark to magnetism? One provocative theory suggests a fraction of dark matter could consist of particles with a minuscule electric charge, a property known as millicharge. These particles would be invisible to light but could still feel the tug of a magnetic field. In the vast, tenuous filaments, such particles could be subtly guided or even accelerated by the magnetic architecture, potentially influencing how dark matter itself clumps and flows on the largest scales. Another speculative idea involves actions, a leading theoretical candidate for dark matter. While actions themselves are not charged in the presence of a strong magnetic field, they could theoretically convert into photons and vice versa. An immense filamentary field could act as a conversion factory, subtly transforming a trickle of dark matter into a faint, detectable radio glow, or perhaps imprinting the magnetic field's pattern onto the distribution of actions. The key word in all of this is speculative. These are not established facts, but intriguing threads of thought spun from mathematical equations. The potential implications, however, are profound. If any interaction exists, it would mean the cosmic web's magnetic fields are not just passengers riding along the dark matter highways, they are active partners in shaping them. The magnetic force could nudge dark matter particles, altering the density of filaments over cosmic time, which would in turn change how and where galaxies form. It would create a feedback loop between the visible and invisible cosmos, with magnetism as the messenger. For now, this remains a captivating hypothesis on the whiteboards of theorists. Proving it will require even more sensitive observations, perhaps from the next generation of telescopes, to see if the glow of magnetic filaments correlates in unexplained ways with the gravitational maps of dark matter. It is a reminder that every new discovery, like this record-breaking magnetic field, does not just answer old questions, it opens doors to mysteries we had not yet dared to imagine. This silent filament may hold more power than we ever suspected. To grasp its true significance, we must place it on the cosmic balance sheet, comparing its energy to the other great forces that fill the universe. The total energy locked within its magnetic lines is staggering, but energy in the cosmos is not measured in simple totals. It is measured in density, the amount of energy packed into a given volume of space. This is the universe's energy budget, and every player has a share. The dominant shareholder, by an overwhelming margin, is the cosmic microwave background radiation. This is the afterglow of the Big Bang itself, a bath of faint microwaves that permeates every cubic centimeter of the universe with a steady, gentle warmth. Its energy density is the baseline, the hum of creation. Next, we have the turbulent motions of hot gas in galaxy clusters and filaments, the churning kinetic energy of the cosmic web in motion. Then there are cosmic rays, those ultra-high energy particles screaming through the void. Where does our magnetic filament fit into this hierarchy? The calculations reveal something profound. While the cosmic microwave background still reigns supreme, the estimated magnetic energy density within this single filament is comparable to, and in some estimates may even rival, the energy density contained in all the cosmic rays and the turbulent motions of the gas within that same vast volume. Think of that. The invisible, structured force of magnetism may hold as much sway in that space as all the chaotic violence of colliding gas and every single one of those unimaginably energetic particles. This is not a minor component, it is a major player, a foundational energy reserve that has been hiding in plain sight, or rather, in plain darkness. If such fields are common throughout the cosmic web, then magnetism ceases to be a curious side effect of astrophysics. It becomes a fundamental pillar of the universe's energy architecture, a silent partner to gravity in shaping how structures evolve. Its energy could regulate the heating and cooling of intergalactic gas, slowing down the formation of stars by keeping the fuel too hot to collapse. It could store energy from ancient cataclysms like vast supernova explosions and release it slowly over billions of years, acting as a cosmic battery that smooths out the violence of the universe. The balance sheet of creation is being rewritten. We are learning that the empty spaces are not empty. They are charged with a potent, structured force whose quiet persistence may have done as much to sculpt the cosmos as any brilliant explosion. That faint magnetic whisper could be a message from the dawn of everything. If this field is truly primordial, a fossil from the universe's infancy, then it is not just a structure in space. It is a time machine. Its very existence and the specific properties we can measure today act as a time capsule, carrying encoded secrets about physics in the first unimaginable fractions of a second after the Big Bang. To read this message, we must look at two key features: its strength and its remarkable coherence. Why would a field from the beginning still be so neatly aligned across millions of light years? The leading theory points to a pivotal event called cosmic inflation. This was not an expansion like any other. In the tiniest sliver of time, the universe is thought to have ballooned from smaller than a proton to a size larger than our observable cosmos today. This violent, hyper-fast stretching would have done something profound to any quantum magnetic seeds present. It would have smoothed them out, ironing them into a coherent, large-scale pattern, much like stretching a crumpled sheet of plastic wrap makes it smooth and uniform. The vast, ordered field we see in the filament could be the direct imprint of that inflationary stretch, a frozen snapshot of the universe's most explosive growth spurt. The field's strength is another clue. If it was generated during inflation or in the turbulent plasma of the very early universe, its initial power would have been set by the energy scales of that era. As the cosmos expanded and cooled, the field would have weakened, diluted by the increasing volume of space. By measuring its present-day micro-Gauss strength and working the physics backward, cosmologists can place limits on what those early energies must have been. This is like finding a faded, ancient letter and, by the faintness of its ink, deducing how bright the light was that originally bleached it. Furthermore, the field might hold evidence of other cosmic milestones like phase transitions. As the hot, dense early universe cooled, it may have undergone sudden shifts in state, similar to water freezing into ice. These transitions could have released immense energy and generated magnetic fields as a byproduct. The specific pattern of the field we see, whether it is smooth or shows subtle twists, could be the signature of such an event. Each property is a line of code in a program written 13.8 billion years ago. Deciphering it could tell us what forces were unified, how symmetry broke, and what the true vacuum of space-time is like. This is not merely studying a magnetic field. It is archaeology at the scale of creation, using the largest structure ever detected as a tool to listen for echoes from the first moment of time. The search for this cosmic whisper is more than a quest for knowledge, it is an engine for invention. To hear the faint hum of a magnetic filament across 10 million light-years, scientists had to become masters of noise. They developed algorithms of breathtaking sophistication, not just to listen to the universe, but to meticulously separate its overlapping songs. This digital archaeology, born in supercomputers processing petabytes of radio telescope data, is now finding powerful echoes in our daily lives. The same core techniques used to filter out the Milky Way's brilliant glare to reveal the filament's subtle pattern are revolutionizing how we see inside the human body. Magnetic resonance imaging, or MRI, is a direct descendant of this physics. While a hospital scanner uses a powerful local magnet, the challenge of constructing a clear image from raw radio frequency signals is profoundly similar. The advanced signal processing methods honed in astronomy, techniques for pulling a coherent picture from a sea of noise, are being adapted to make medical scans faster, sharper, and more detailed. This means doctors can detect smaller tumors, map brain activity with greater precision, and reduce scan times for patients, all because astronomers needed to see the invisible structure of the cosmos. The impact extends beyond medicine. Consider remote sensing, the science of observing Earth from satellites or aircraft. Our planet's surface emits a complex jumble of signals across different wavelengths. Isolating the specific signature of a forest fire, an oil spill, or a mineral deposit from this background clutter is the same fundamental problem as isolating a magnetic filament from the galactic foreground. The algorithms first written for cosmic cartography are now helping monitor deforestation, track climate change, and manage natural resources with unprecedented accuracy. They turn chaotic data into actionable maps. Even the way we store and transmit information bears the fingerprint of this cosmic search. The immense datasets from telescopes like the low-frequency array cannot be stored in their raw, gargantuan form. Scientists had to pioneer new methods of data compression, ways to preserve the essential scientific information while drastically reducing file size. These lossless compression techniques, which ensure no critical detail is lost, are now influencing everything from streaming high-definition video to managing the data clouds that power our digital world. Each time we watch a clear movie online or a doctor views a high-resolution scan, we are benefiting in some small way from the need to listen to a magnetic whisper in the void. This is the hidden cycle of exploration. By pushing our instruments and our minds to the absolute limit to answer fundamental questions about the universe, we are forced to invent new tools. Those tools, forged in the crucible of pure curiosity, inevitably spin off and transform our world. The largest magnetic field ever discovered may seem impossibly distant, but the quest to find it is quietly shaping the future of how we see, understand, and care for our own planet. But the journey to map this magnetic universe has only just begun. The next decade will witness a revolution in our ability to see the invisible, driven by telescopes of such power they will render our current maps mere sketches. At the forefront is the Square Kilometre Array, a project that will redefine the very meaning of cosmic observation. When its thousands of dishes and antennae across South Africa and Australia come fully online, it will create a radio eye of almost supernatural sensitivity. For cosmic magnetism, the SKA will be a revelation. It will not just detect a few prominent filaments, it will conduct a full sky census of magnetic fields. It will trace the delicate magnetic threads within every nearby galaxy, watch how stellar winds and supernova blow magnetic bubbles into intergalactic space, and chart the evolution of these fields from the early universe to the present day. Its maps will have such exquisite detail that we will see the magnetic turbulence at the edges of cosmic web filaments, watch fields reconnect and release energy, and potentially even detect the weak magnetism of the pristine gas between the galaxies. The SKA will turn the faint hum we now struggle to hear into a rich, complex symphony, allowing us to listen to every instrument in the cosmic orchestra. Yet, even this giant has a limitation, one imposed by our own planet. Earth's ionosphere, a layer of charged particles high in our atmosphere, acts like a rippling lens for the lowest frequency radio waves, distorting the signals from deep space. To see with perfect clarity, we must rise above it. This is the promise of space-based radio observatories, a dream now edging toward reality. Missions currently in the proposal stage envision constellations of small satellites forming a virtual telescope in the quiet vacuum of space, far from earthly interference. From that pristine vantage, they could observe the lowest frequencies of all, frequencies blocked entirely by the ionosphere, opening a completely new window on the magnetic universe. These are the frequencies where the most ancient magnetic signals, stretched by the expansion of the universe itself, might still resonate. A space-based array could see the magnetic fields from the first galaxies and quasars in their raw, undisturbed state, offering a direct view of how magnetism shaped the cosmos in its youth. Together, these next-generation tools will transform our understanding from detective work into direct observation. We will move from discovering giants to studying their anatomy, from wondering about origins to watching magnetic fields being born in the shocks of colliding galaxy clusters. The invisible web will finally come into focus, not as a static backdrop, but as a dynamic, living structure that breathes and evolves across cosmic time. This discovery leaves us with a question that echoes beyond physics. What does it mean to live in a magnetized cosmos? For centuries, our view of the universe was defined by light and gravity. We saw the luminous islands of galaxies and felt the silent pull that holds them together. The space between was a void, a backdrop of nothingness. Now we know that void is not empty. It is threaded with an invisible architecture of force, a magnetic web that connects every cluster, every filament, every galaxy in a continuous field of influence. This suggests a universe far more interconnected than we ever dared to dream. The galaxies are not isolated islands. They are nodes in a vast, thrumming network, linked by lines of silent power that guide gas, steer particles, and perhaps even whisper to the dark matter itself. It is a cosmos alive with unseen dynamics, where forces we are only beginning to map shape the destiny of everything we see. This adds a profound new layer of complexity and beauty to our understanding. Beauty is not just in the glittering stars, but in the elegant, hidden order that orchestrates them. The universe is not a simple place growing more chaotic. It is a place where order emerges on the grandest scales, where chaos gives birth to coherent structure, and where something as fundamental as a magnetic field can be woven into the fabric of existence itself. We are moving closer to seeing the universe in its full, multidimensional glory. We are learning to perceive not just with our eyes, but with instruments that sense the push and pull of forces in the dark. Each new layer we uncover, from dark matter to dark energy to this cosmic magnetism, reveals a cosmos of staggering sophistication, a masterpiece with more dimensions than we once thought possible. To know that we are part of this intricate, magnetized web is to find a new, humbling, and magnificent place within it. We are not just observers of a distant stage. We are embedded within the living machinery of the universe, breathing its magnetic breath. This magnetic web is not a cosmic threat or a message from another civilization. The sheer scale of this discovery can easily spark wild speculation, so it is crucial to separate the breathtaking science from science fiction. First and foremost, this field poses absolutely no danger to Earth or our solar system. Its unimaginable size is matched only by its incredible weakness. Remember, it is 1,000,000 times fainter than the magnetic shield that already harmlessly envelops our planet. We are not being enveloped by some alien force. We are simply learning that the void has always had a subtle texture we could not previously detect. Furthermore, this is not evidence of some ancient galaxy-spanning intelligence. The structure is awe-inspiring, but its origins are firmly rooted in the natural laws of physics, whether from primordial seeds or the dynamo action of flowing gas. The patterns we see are the result of immense, impersonal forces acting over billions of years, not the blueprint of a cosmic engineer. There is a profound difference. Finding a perfectly hexagonal basalt column formation on Earth fills us with wonder at nature's artistry. We do not immediately attribute it to giants or gods. This magnetic filament is a natural formation on the grandest possible canvas. Finally, this discovery does not break or violate the known laws of physics. It challenges them, it stretches them to their limits, but it does not shatter them. In fact, its existence was predicted by theories and simulations long before we had the tools to see it. This is how science progresses at its best. A prediction made in the quiet of a theorist's office is finally confirmed by a telescope a generation later. The real wonder is not that we have found something impossible, but that we have found something perfectly consistent with a universe even more magnificent and interconnected than we supposed. The truth is more compelling than any fiction, a silent force woven into the architecture of everything, waiting eons for us to learn how to see it. The challenge lies in translating that faint radio whisper into a map we can see. To bridge that gap, let us propose a visual segment for our video, a journey into the data itself. Imagine the screen shifting from a star field to a dynamic, animated simulation. We are no longer looking at points of light, but at a flowing visualization of polarized radio waves. Each wave is represented not just as a ripple, but with a tiny arrow showing its precise orientation. These arrows are called polarization vectors, and they are the critical clue. In the simulation, we see a region of space that looks dark and empty to our eyes. But as the animation begins, these vectors start to appear, not randomly, but aligning themselves into clear, coherent patterns. They flow in gentle curves, they form sweeping arcs, they create vast, swirling patterns across millions of light years. This is the direct translation of what telescopes like the low-frequency array measure. Each arrow's direction tells scientists which way the magnetic field is pointing at that exact point in space. Its length hints at the field's strength. It is the cosmic equivalent of sprinkling iron filings around a bar magnet, but instead of a tabletop experiment, the magnet is 10 million light-years long, and the filings are the polarized light from ancient electrons. The animation would make the invisible tangible. We could watch as the algorithm processes the raw, noisy data, a chaotic snowstorm of arrows. Then, as the statistical magic works, the noise fades and the underlying order emerges, revealing the majestic magnetic architecture of the filament. It would be like watching a ghost slowly materialize, its bones made of lines of force. This visualization invites you to trace those lines with your mind's eye. Start at the edge of one galaxy cluster and follow the flowing vectors out into the darkness. They do not break or scatter. They guide you like luminous threads all the way across the abyss to the next cluster. You are not looking at a picture of a magnetic field. You are seeing the magnetic field itself, translated into a language of light and motion. This makes the abstract profoundly concrete. It transforms a micro-Gauss measurement from a line in a scientific paper into a living, breathing structure you can almost reach out and touch. It shows that science at its best is not about cold numbers, but about revealing the hidden patterns of reality, about giving us eyes to see the forces that truly hold the cosmos together. That faint hum in the void is a single note in a grander composition. Our journey began with a record, the largest magnetic field ever discovered, a filament of force spanning 10 million light-years. We traced its origins to a cosmic crossroads, debating whether it was a primordial fossil from the Big Bang or a self-made engine born from the flow of the cosmic web. We measured its whisper-weak strength and calculated the staggering total energy it commands, a reservoir rivaling the violence of cosmic rays and turbulent gas. We saw its hidden hand potentially guiding the birth of galaxies, accelerating the universe's most energetic particles, and perhaps even conversing with dark matter itself. This is far more than a new entry in a record book. It is a fundamental clue, a direct signal that magnetism is woven into the universe's largest structures. It tells us the cosmos is not just held together by gravity, but also threaded with an invisible architecture of force, a hidden symphony playing on strings of unimaginable scale. This discovery reframes our entire reality. The empty spaces are not empty, they are alive with silent, structured power that has been shaping everything we see from the very beginning. Our quest to map this invisible web is a testament to a uniquely human kind of curiosity. We built instruments to hear whispers across the abyss, wrote algorithms to filter out the noise of creation, and persevered until the ghost in the machine revealed itself. We are not just stargazers, we are cartographers of the unseen, learning to read the universe in wavelengths beyond light, to feel the push and pull of forces in the dark. Each new map we draw, each filament we trace, brings us closer to hearing the full symphony of the cosmos and understanding our own place within its magnificent magnetized score.